Similar to the warm-up we just did, we're going to be working with two variables today, which feels familiar from other math classes, but unfamiliar from what we've been doing in this class. In Chapter 3, we talked about numerical summaries and a little bit more graphical displays with the box plots of single variable data. And for a lot of you, your projects are single variable data projects. But for some of you, you have bivariable data, which means you have two variables going on. And so I need to show you how you can display two variable data. And again, this is going to feel familiar from functions classes, so college algebra, algebra 2, algebra 1, pre-cal, all of those things. But we're going to just start off with an example. An economist wants to determine the relation between one's FICO score and the interest rate of a 36-month auto loan. Do y'all know about credit scores?
Yeah, I got a 320.
I'm scared for you. The given data represents the interest rate a bank would offer on a 36-month auto loan for various FICO scores. So FICO scores or credit scores range from 300 points to 850. The higher your credit score, the more dependable you have proven to banks that you are in paying back money they lend you. So as you take out loans for school and pay them back, your credit score will go up because you're showing the bank, hey, look, you loaned me this money and I'm giving it back to you at the appointed time. I'm paying my bills on time. I can be trusted with credit. I don't have too much debt in any sort of way, credit card debt, school debt, all of those sorts of things. I have an appropriate amount and you pay back your stuff. So we have these 6 data points here where somebody with a 545 credit score got a loan of 18.982% on this 36-month lease for a car, all the way up to 750 getting a 5.15% interest rate. So let's first use Excel to plot a scatter diagram for the data and then find the sample correlation coefficient. So you guys can start typing this data in, and what I want to know is how the trend of this data would look if we were to sketch this on our paper. Once we have our data typed in, you're going to select the bivariate data, so both columns of data, and you're going to go to Insert, Scatter Plot. Now, just because this is class and we're not trying to display this data, let's just get rid of the chart title and the series so we can just look at the information. But also remember, credit score goes all the way from what number to what number? What does it say on your paper?
3 to 8.
So should my graph on my paper display from 0? No, what should be the minimum value? 300. So if I double click the horizontal axis, it'll take me to the horizontal axis and I can change the minimum to 300 and the maximum to 850. And that way it's just a better display of our data so we can make some conclusions here. So on my paper, just because I think it's a good habit, I've given a sketch of what this scatter plot looks like. A sketch is fine. You have the actual data on your computer screen that's part of your notes. But just so you can look back later just at the paper, let's give it a scatter plot sketch. Now, without using fancy statistical knowledge, what can you tell me about the data in this scatter plot? What are some things you know? That it's decreasing. What kind of association would that be? A positive or a negative association? Are those dots spread out or pretty close? Pretty close. So you would say there's probably a strong negative correlation here. And in Algebra 1, Algebra 2, pre-cal, that was fine at this point just to say that because you can visually see from the dots. However, this is statistics. So we need actual numbers to back up our claims. And so what we're going to do is we're going to actually calculate the correlation coefficient and determine if that number is strong enough for that sample size to be considered a linear relation. What I mean by that is we're going to go and actually do like you did on the warm-up, and we're going to calculate the correlation coefficient. So for R, it's equals cor L, open parentheses, and then array 1 and array 2, which is what the hint is telling you here, just means select all of the inputs and then all of the outputs. I like to do the outputs first, just so that it's similar to when I do the trend line. So I select all of them, comma, all of them. Doesn't matter if you do inputs or outputs first, but I like to do outputs, comma, inputs. What did we get as the correlation coefficient? Negative 0.976. We'll just round it to 3 decimals. That's a pretty good habit, is to always round the correlation coefficient to 3 decimals. But if it tells you to round a different way, you round a different way. In a previous course, if you had actually found the correlation coefficient, look what kind of number you have. It's a negative number, which is why we saw a negative association. What number is 0.976 pretty close to?
Uno.
-1, which means it's really strong, which is what you saw from the data to begin with. But again, because this is statistics, I need you to actually back up your information and your claims. What we're going to do is we're going to use the table of critical values for R, the thing I told you to ignore on your warm-up, that table of critical values, we're actually going to have to use it. And the way that you use that table of critical values from your warm-up is looking at the sample size. How many credit scores are in our sample for this study? 6. So on your table, look at your paper. I can't show you it because I don't have it pulled up. On your paper from your warm-up, the table where it says n equal to 6, what does it say is the critical value associated with n equal to 6? Okay, so here's what we do to back up our claim. We look at the absolute value of our correlation coefficient. What is the absolute value of negative 0.976? Don't overthink it. Yeah, the positive version of that, right? Is that number greater than or less than 0.811? Greater than. If that number that you get as the absolute value of your R value is bigger than the critical value, you actually can claim with proof that this has a linear relationship. Now, the book has you answer this sentence that was weirdly worded, so I've put it here so we can practice. We would say that because the correlation coefficient is a negative number and that the absolute value of R is 0.976, since that number is greater than the critical value for this data set, which is 0.811, we can claim that this negative linear relationship exists. If we had had a positive R value, only two things would change here. We'd say it's positive in our linear relationship here and here. That was not a good explanation, but you get it. If we had drawn our inequality the other direction where the critical value was bigger than R, you'd have to say there is no linear relationship. Your R value needs to be bigger than the critical value from the table. This table does not change, so I've given you this paper copy, but it also pops up. You know how our homework has those like pop-up menus? It will pop up the table for you every time, so if you lose this piece of paper, not a big deal. You can also Google, because this is a thing that statisticians have created. You can find a table for R values anywhere. Make sense? Okay, cool. So let's just talk about this in terms of like the experiment itself. Do you think that a change in a credit score causes a change in the interest rate? Yes or no? Yeah, that's one of the, actually in real life, that's one of the main ways that banks and lenders will decide if you're worthy of a loan, if you're trustworthy enough for a loan, and what kind of loan with an interest rate they would give you. However, there are some other lurking variables in this study that we need to think about. Remember, this is us trying to do a 36-month auto lease. What are maybe some lurking variables in this study? Income, absolutely. If you have a steady income, if you have a steady job, you're probably going to be more likely to get a better interest rate because the bank thinks they can trust you more. What are some other things? Say again? Yeah, what type of car it is. If we go to Lamborghini versus going to Honda, we're probably going to get a different interest rate even with the same credit score. I thought of one more. And let's think about this in terms of like if you and I both go to Honda and we're like, we want a CRV. And Honda's like, cool, here's the loans for each of you. Here's the interest rate on your loans. Who's probably going to get a better loan interest rate, you or me? Why? Because I'm older. Age is definitely something that's a lurking variable in the scenario. I've had more time to prove that even my credit score has stayed at a good credit score than your credit score because you're younger. Does that make sense? Those are the three I thought of. Can anybody think of another one? I can't hear you, I'm sorry.
Like a house?
Whether you own a home, that would have to do with your credit score because having a house payment is a part of your credit score. So like, yes, but that leads into credit score. Anything else? Somebody in my last class said like geographic location, and I was like, explain. And they're like, well, if you're in Alaska and you're getting a Tesla versus a Tesla in Dallas, like it's kind of dumb to get a Tesla in Alaska. And I was like, honestly, great point. So maybe geographic location could potentially change some things, which also turns into type of car. But it's a good idea of the lurking variable. If there are not a lot of cars for sale in your area, it's going to be more competitive to get a lease, get a car. Totally agree. Let's leave that for a second. So we're going to create a trend line called a least squares regression line for this data. Now, I know I previewed this with you on the warm-up. This is your Y1 squiggly line in Desmos. This is your stat edit on the calculator. You notice there that no matter what class you learned to do this in, you are always creating these regressions with technology. Because creating a least squares regression line is actually really complicated. As in, it would probably take us 3 or 4 pieces of paper to do it. So instead, we're going to always use technology like we've done in the past classes to do this. You can use stat edit. You can use Desmos, Y1 squiggly line. But we're practicing in Excel, so what we're going to do is go to Excel and find the equation for this data for our least squared regression line. If I'm showing you mine, so I'm going to find the least squared regression line by doing equals line ST, and then it's asking me to put in the y's first, so I select all of the y's, comma, then the known x's, so I go to the input values or the explanatory variable, and then I press enter, and what it's going to do is it's going to give me the slope in the first cell and the y-intercept in the cell next to it. And if we're rounding these to 3 decimals as well, our least squared regression line would be y equal to negative 0.076x plus 61.369. We're just going to round to 3 decimals. I know I'm not showing you what I'm writing. Let me switch it over. Now, if you're thinking to yourself, why do you keep putting that weird symbol above y? Does anybody who took my AP class last year remember what that's called? It's a Y hat. You literally call it Y hat, which I think is adorable. It's called a Y hat. It's basically telling me that the output predicted by this line is actually a prediction, not a real value. So Y hat is our, like, this is a Y sort of. It's got a little hat on it, a Y hat, if you will. Now in this equation, just to make sure we remember this, our outputs are interest rate, given as a percentage, and our input is our credit score. And I'm bringing that up only because this next question requires you to remember what we're even doing in the first place. It says, what is the predicted interest rate? So we want Y hat for someone with a credit score of 730. Where do we put the number 730? On the X. So I'm going to go into either on a calculator or Excel, which I would like for you to practice on Excel. And I'm going to do Y hat equal to negative 0.076 times 730. Plus 61.369. Now, times in Excel, you cannot just let it assume putting a parentheses will mean multiply. It does not. You have to put the little asterisk symbol to mean multiply. So if I was doing this in Excel, I would type in a random cell equals negative 0.076 times 730. Plus 61.369. So times, not parentheses. Times is with the asterisk symbol. When you calculate this, what do you get? 5.889. So 5.889% is our predicted value for a credit score of 730. Now, the following question goes with this one. It says someone with that 730 credit score did actually apply for a loan and was legitimately offered an interest rate of 6.1%. So is that above or below average, and by how much? Yeah, 6.1 is a bigger number than this one. Our predicted value is smaller than the actual value. So we would say that that value is above average, but we need to figure out by how much. And so what we're going to do is we're just going to simply subtract those two numbers. So we're going to do 6.1 minus 5.889. You can do this in a calculator or in Excel, but it's a simple subtraction problem. I'm going to assume we can do that. This is 0.211%. So it's an above average value, because average is my trend line, is my line of best fit for the data. But seeing immediately that our trend line does not actually reflect the actual data points for every single time, what we need to do is understand how to create or calculate the error in our least squared regression line. The error in our least squared regression line has another name. It's called the residual value. Those of you who are in AP should remember that. Here's how we're going to, this has two questions, so I'm going to do the first one, you'll do the second one to make sure you understand how to do it. We're finding the error in a least squared regression line based on a credit score of 640. Notice 640 is in my table. Look up at the table at the top of this paper. What is the interest rate for a 640 credit score? So we want to calculate, based on our trend line, on our least squared regression equation, what it would give me for 640 and see how far off it is. That's called a residual. So what we're going to do is we're going to calculate y hat. Y hat is going to be equal to 0.076 times 640 plus 61.369. We would calculate that. I'm going to trust that you can do it, is 12.729. And if we're finding the residual, which is the error, the formula we use is the actual value minus the predicted value. I just put an equal sign. Actual value minus the predicted value. So if we're finding this error, the residual, we would literally just subtract the actual data point you guys told me in the table, 12.218, and I'm going to subtract 12.729. The actual data point from my table minus the predicted value I got when I plugged in that number. And our residual here, the error would be negative 0.511, which is considered an overestimate of the true value because our predicted value was bigger than our actual value. So a negative number gives you an overestimate. A negative residual, gives you an overestimate. Now I did all of that without giving you a show of how to actually calculate them. So the second part is for you. This is the second question here. It says, what is the error in our least squared regression line on a credit score of 750? So I need you to calculate 750, and I need you to compare it to the actual data for 750 in the table. I'll give you some time. Here's the next little part here, and this question is very interesting because in terms of classes you've taken before, this question is very simple. It says, would it be appropriate to use this model to make a prediction for somebody with a credit score of 400? What will you do with the number 400? You just put it in there, you'd get a number out. However, this is a statistics class. Look back at the actual table we have. What's the lowest value we got as a credit score? What's the highest? We can only make predictions within that range. We can't make predictions that extrapolates the data below or above our actual data points. So to actually answer this question, would it be appropriate to use this model? Since this is a stats class, the answer is no. 400 is outside the scope of the data. If we had had a data point at like 300, we could have done 400 because it's within the scope of our data. But since our lowest value was 545, we can't expand that below 545 or eventually above 750. It's outside of the scope of the data. Now, if this was a like regular linear class, a functions class, yeah, you plug in 400, you get an output, but this is a stats class. We have to stay within the bounds of our data. And this next question is also very interesting. It leads us on to this question. What do the slope and the y-intercept of the least squared regression line mean in context of this problem? Okay, easy slam dunk question. What is the slope of this line? Look back at question, well, I didn't number these. Okay, yes, I heard it. Boom. Now, what does that mean? Because we can't just give numbers and not understand what we're talking about in stats. We have to back up our information with explanations. What is the input value again? No, sorry. What are we plugging in? Credit score. What are we getting out? And then since this slope is negative, does that mean every time we change the credit score and increase it, is the interest rate going to go up or going to go down? By how much? By that much. Very good. So the slope, remember, tells us, or this number means for each credit score, credit point added to your score, the interest rate should go down. That's not how you spell should. By 0.076 of a percent.
So why would it go down? Sorry, this is just me not knowing. Why would it go down if you're adding?
That's a great question. Why would it go down if you're adding the number? Remember that we have a negative trend. So as credit score increases, interest rate goes down. Also, the slope is negative. Down. Okay, let's look at the second question, which is honestly a more interesting question. It says, what is the y-intercept in context of this problem? What is the y-intercept here? 61.303, what? Hello. 61.369. And what does it mean in this problem? It starts off with, when we've plugged in what credit score, we get this number. Y-intercepts are always partnered with what x value? 0. So what credit score would we plug in here? 0. So when we plug in a 0 credit score, we get 61% as their interest rate. But hopefully that's like a record scratch for you. Something's wrong with that sentence I just said. What's the lowest credit score you can have? 300. So can I plug in a credit score of 0? No. So in fact, and this is why this is an interesting question, the y-intercept is 61.369, but it means nothing in context of this problem because you can't have a 0 credit score. The lowest credit score you can have is a 300. A credit score of 0 is impossible.
Never say never.
Okay, look, I knew somebody was going to do it. Credit score of 0 is impossible. Lowest you can get is 300. So this y-intercept, it is a y-intercept, but it means nothing in context of the problem. So we need to make sure while we're doing these problems, we're thinking about what they're representing because it matters. Yes? Okay, on the back is just some vocabulary for you, some things I want to point out here before you try an example problem on your own. We talked about scatter diagrams this whole time. They are the coordinate point scatter plots that you're used to seeing. This is always for our 2 quantitative variables. So if you are doing a study for your project that's only 1 variable, you should not be giving these scatter plots. Doesn't make sense. This is for 2 variable data. But the one thing I want you to notice is that the explanatory variable acts as your input and the response variable acts as your output. So explanatory variable is input, response variable is output. You guys naturally understood this next definition of the linear association. The linear association says that as one variable increases, the other increases, meaning we have a positive linear association. Or a negative linear association is as one increases, the other decreases, which is like our credit score and interest rate. And once we have these linear associations, we can also measure the strength of them with the correlation coefficient. That's the R value that you're finding. It tells you the strength and direction of the linear association. Notice we can have a perfect positive association where the dots are straight up in a line. That would be a linear function. But if they're not quite in a line, but pretty grouped in a line, let's say strong positive, look, notice the R value is still pretty big. But as the data points get wider and further away, the R value gets smaller. So it's still positive, there's still a correlation, but it's not as strong as the other ones. Same vibe the other direction, we can have a perfect negative association. It can have two different strengths. And depending on the sample size, you could determine if it's a yes or a no. Remember the table of critical values? Or we can have no linear association, which is when they're all over the place, or it's like a curve. That looks like a quadratic to me, am I right? That's not a linear association anymore. There might be a quadratic association. We don't deal with that. Now, again, we have this critical value. This is the table that you're going to need to pull up and use each time. You have to compare the sample size, the N, to determine if the R value is strong enough to confidently say, yes, it has a linear relationship, or no, it does not. That's what you're looking for. And then last but not least, the least squared regression line. Here's why we don't do this by hand. It says the least squared regression line is the line that minimizes the sum of the squared errors or residuals, meaning you'd have to find that residual, y minus y hat, for every data point, and do that for a bunch of different trend lines until you figure out the one that has the least sum of the squares. I don't want to do that by hand, do you? That's why we use technology. It minimizes the squared vertical distance between the observed values and the predicted values, y hat. We will use technology to find these lines of best fit. If you go home and you absolutely do not like using Excel to do this, remember this is stat edit on a calculator. Or if you're a Desmos person, it's Y1 squiggly line. Those are all finding the lines of best fit. And you can use them as long as you know how. I'm going to be teaching you on Excel.
Did you ever have to do them by hand?
I remember one time doing it by hand and then them being like, this sucks, right? And you're like, yeah. And they're like, cool, you stat edit. I'm like, great. Thank you so much. Okay, this check for understanding is for you. I want you and the people next to you to work on this one. This sodas example. There's only 4 parts. I'm going to slowly put my answers up on the board, but I want to see if you can get them first. When you're done with this, we're done for the day. Okay, I've had a couple questions about the part B, so I want to just say it out loud so everybody can clarify this one. We all got the trend line and the R value pretty easily, yes? But then it's how do you use these numbers and where did they come from has been the question I've heard. That's a great question. N equal to 15 means I counted how many data points I had, and I had 15 rows that I was using. I had 15 dots on my scatter plot, if you will. So my number of my sample size is 15. And then I look at the table of critical values to find the number next to 15, which is 0.514. Since the absolute value of my correlation coefficient is bigger than that critical value, that's when I can say yes. If the absolute value was not bigger than the critical value, you'd have to say no. But we can say yes. Last but not least, let's talk about C and D. Would it be reasonable to predict the bone density for someone who drinks 15 colas per week? No. Why not? Correct. 15 is outside the scope of the data. It wouldn't be a reasonable prediction. Then the last question said, someone outside the study reports drinking 4 colas per week and has a bone density of 0.895 grams per centimeter squared. Is that above or below average? Okay, well, I want to use my average line or my least squared regression line to see what the y hat should be. So what I would do is I would take this number 4 and I would plug it in for the number of sodas per week. And I would get the number 0.874. That's my average based on the least squared regression line. So comparing it to this data that the person actually reported, is that the actual data above or below average? Above average, and I think I have a...
The average is, which one is the average?
This is the average. So the data point that I was given was 0.895. That one is bigger than the y-hat predicted value. So the person who reported 4,0.895 is above my average, because my average is the trend line. Now, that's not asking you what's the error. That's asking you, is that reported value above or below average outside of the study? Someone outside the study, not from the table, outside the study. You could find the error by looking at the 4 in the table and then calculating. That's not what it asked for. It asked for outside of the study, gave you a data point, and asked comparing to the trend line, is that above or below average? That's a good question.